This video is on section 8.2, a single population mean using the student's t-distribution. So there's going to be a link in Canvas to this YouTube video about the student's t-distribution. It can be helpful because it tells you where it came from, how it was developed, and how to use it. But basically, we often don't know the population standard deviation. If the sample size is large, you can use the sample standard deviation S as an estimate for the population standard deviation sigma. But if it's not a large sample, you get inaccuracies in your confidence level. So the student's t-distribution helps you take care of this issue. Then we have the t-distribution, and here's our notation. T is a random variable with a t-distribution, and the degrees of freedom would go down here. And df is degrees of freedom, which is n minus 1. And n minus 1 is 1 less than your sample size. So n is your sample size, and the degrees of freedom are n minus 1. So properties of the student's t-distribution. The graph for the student's t-distribution is similar to the standard normal curve. The mean for the student's t-distribution is 0, and the distribution is symmetric about that mean, that 0. And the student's t-distribution has more probability in its tails than the standard normal distribution because of the spread of the t-distribution is greater. So the graph of the student's t-distribution will be thicker in the tails and shorter in the center than the graph of the standard normal distribution. So here's a picture. Z, the blue one, is our standard normal distribution. The red one is our t-distribution with a sample size close to 30. And the green one is a t-distribution with a smaller sample size. So you can see that as our sample size gets bigger, this red curve is getting closer to the blue, which is the standard normal distribution. The exact shape of the student's t-distribution depends on that degrees of freedom, on the sample size. As the degrees of freedom increases, the graph of the student's t-distribution becomes more like the graph of the standard normal distribution. We just saw that in the picture. The underlying population of individual observations is assumed to be normally distributed with an unknown mean mu and standard deviation sigma. The size of the underlying population is generally not relevant unless it's very small. We're assuming that there's random sampling, but that's a separate assumption from the normality of our original population. And here's another picture again, and this just has a few more of the degrees of freedom shown. And so the teal one is the standard normal. And then the higher the degrees of freedom are, the closer the graph is to that standard normal. So degrees of freedom here is 1, and you can see it's the one that's sort of the furthest away from our standard normal graph. So the degrees of freedom, n minus 1, come from the calculation of the sample standard deviation S. This calculation requires n deviations, and remember, deviations are how far each value x is from the mean. Because the sum of the deviations is 0, we can find the last deviation once we know all the other n minus 1 deviations. The other n minus 1 deviations can change or vary freely, and we call the number n minus 1 the degrees of freedom. The t-score is very similar to the z-score. It measures how far away our sample mean is from our population mean mu. And the formula for the t-score is x bar minus mu divided by this new standard deviation that we're going to use, which is the sample standard deviation divided by the square root of the sample size. And we're going to use this command, the t.inv command in Excel. It's 1 minus the confidence level. So remember, this is our alpha value divided by 2, 1 minus that, and then our degrees of freedom. So in Excel, I have, in Canvas, there's an Excel sheet. So we're just going to pop over to that, and we're going to calculate this t-score. So we're going to do t.inv, the probability. So we're looking for the 95th. The t-score for the 95th percentile. So 1 minus, and in this case, it's going to be 0.05 divided by 2. And remember, this 0.05 is 1 minus our confidence level here. So it's 5%, so 0.05 divided by 2, 1 minus that, and then our degrees of freedom. So if our sample size is 22, our degrees of freedom is going to be 21. So that's our t-score, 2.07961. So our first example, try at 8.8. We do a study of hypnotherapy to determine how effective it is in increasing the numbers of hours of sleep subjects get each night. We measure the hours of sleep for 12 subjects with the following results. So down here is our data. These are all the hours of sleep of our subjects that they reported. We're going to construct a 95th percent confidence interval for the mean number of hours slept for the population, which we're assuming is normal, from which we took the data. So over in Excel, I have our data listed here. Okay. So we know that we did 12 subjects, but I just wanted to show you that if you didn't know off the top of your head how many you had, this count A formula in Excel counts the number of cells that are not empty in the range that we choose. So I can highlight all of our data and hit enter, and it tells me there's 12. Now, if you had letters and numbers and you wanted to count just the letters or the numbers, you'd have to use something different because count A just tells us how many are not empty. You can also just type the number 12 in here. So X bar is our sample mean. So we're going to calculate that. In the previous section, we were given the mean, the sample mean. Here we're going to calculate it. So I'm going to use the average function, highlight all my data, and that gives me my sample mean, my average for the data that I collected about the mean number of hours slept. So now our t-score. So we just calculated that over here, but I'm going to type it in again. t.inv, the probability, so that's going to be 1 minus 0.05 divided by 2, and the degrees of freedom. So that's different here. So our sample size is 12, so our degrees of freedom is going to be 11. So you can see that they're a little bit different because the degrees of freedom is different. So our standard deviation, so S is the sample standard deviation. So remember, when we do our standard deviation, we have a couple of different options. Make sure you pick the sample standard deviation formula and then highlight your data. That tells us the sample standard deviation for this sample. And now we're going to calculate that standard deviation divided by the square root of our sample size, which again is 12. Now you can type in 12 or you can reference your cell, whatever you want to do. Now we're going to calculate the EBM the same way we did when we were given the mean and we knew the standard deviation. So the error bound for our mean is going to be our t-score, I clicked the wrong one, times that standard deviation. Okay, so our error bound for our mean is 0.81988,581. And then for our interval upper bound, same thing that we did before, we're going to take our mean and we're going to subtract off our margin of error. And then for the lower bound, we're going to take our mean. Oh, I did subtracted the first one. Sorry, this should be the subtraction one. And then this one for the upper bound, I need to add it. Apologize. All right, so for the upper bound, take your mean and add on your margin of error. For your lower bound, take your mean and subtract off your margin of error. So this is our confidence interval here. And if we go back to the slides, we have our N value, our sample mean, our t-score, our sample standard deviation, our error bound. So here it is mathematically, the t-score times our standard deviation divided by the square root of our sample size. So that gives us our margin of error or error bound for our mean. Subtract it off, add it to our mean. Here's our confidence level interval. And we say we are 95% confident that the true population mean number of hours slept is between 8.2 and 9.8 hours. So it's the same. There's a lot that's the same in this section compared to the first section, 8.1. What's different is that we're going to calculate the sample mean, and we're going to calculate the sample standard deviation, and we're going to use a t-score instead of a z-score. So another example, a random sample of statistics students were asked to estimate the total number of hours they spend watching television in an average week. The responses are recorded below. So here are the number of hours spent watching TV in an average week. We're going to use this data to construct a 98% confidence interval for the mean number of hours statistics students will spend watching television in 1 week. So go back to Excel. We have the data in here. Move my face. So N, again, so we might know how many students we've sampled, or we can use that count formula again. So does it tell us here? It doesn't tell us how big our sample size is. So I'm going to use the count function. Count A. It's going to tell me how many individuals I have in that sample, 15. I'm going to calculate the average for that sample. I get an average number of 6.13 repeating. I'm going to calculate my t-score, so t.inv. So the probability this time, we're looking for the 98th percentile, or confidence level. Sorry, I'm getting my words wrong today. So 1 minus 0.02 divided by 2. Because it's the 98th, our confidence level is 0.98. 1 minus that for alpha is 0.02. Divide that by 2, subtract from 1, and then our degrees of freedom is going to be 1 less than n. So I'm actually going to do this minus 1, because that's just another way to put that degrees of freedom in. And I get a t-score of 2.62. Our sample standard deviation, remember, make sure you pick the sample one, not the population one. You remember you get slightly different numbers if you do the population versus the sample one. And then the standard deviation that I'm going to use, I'm going to take the number I just calculated and divide it by the square root of our sample size. So our error bound, our margin of error is going to be our t-score times that standard deviation. Our margin of error is 3.74. Take our mean value, 6.133, add our margin of error to get our upper bound for our confidence interval, and then take our mean and subtract off our margin of error for our lower bound. So this is our confidence interval here. And back on our slide, here's all our information, our statistics. And we can say we are 98% confident that the true population mean total number of hours watching TV is between 2.4 and 9.9 hours. So that is the end of the video for section 8.2 on the student's T distribution.